Yeah. So I'm ready myself.
Okay, one moment. Okay, we can start. Sorry.
Fine. So thank you very much again for the invitation and for the patience to listen me. And that's basically to do it in a completely independent way with respect to the first talk. So let me start with the very beginning. What is the aim of this talk? So don't hesitate to stop me, to interrupt me, to ask me questions, and to ask for more details if you want to. So the aim is to study some surjective homomorphisms. Surjective morphism from a surface group pi1 of sigma g. Generally speaking, G is at least 2, but sometimes you don't really need this, but from obvious reasons. So from pi1 of a closed oriented surface of genus G into some group G. And I want to study this homomorphism up to an equivalence relations up to let's say the so-called Hurwitz equivalence, which can be stated into two ways. So either you take the outer automorphist group of pi1 of sigma g, and sometimes if I want to be close to the topological definition of this outer automorphist group, I put some plus here corresponding to the fact that these are the outer automorphists of the fundamental group, which are induced from homeomorphism reserving the orientation of the surface sigma g and preserving a point on the surface up to isotopy, preserving this out point. So this is acting on the left, on the if I'm adding G. So so this action is on this homomorphism, which are surjective from pi1 of sigma G into G. And as I said, G here is acting by conjugacy on the right side, and then this one is acting from the left side, so on pi1 of sigma G. So this can be also encoded most of time by an action of automorphist group. Again, I'm putting this plus, but most results do not depend on this plus. So you take just the full automorphist group of pi1 of sigma G acting on left. On the left side. So that's the usual action. So we have to remark that in the first talk, I was interested in a similar situation coming from branched covering of surfaces when G is a finite group, and also when G was a braid group, we had the so-called braided surfaces, and in this case, I have looked instead to homomorphism from F from phi1 of sigma G minus a finite set of points into G. So B is a finite branch set, finite branch set. And we can do similar things, but there loops around these points. I'm fixing some base point here. I'm taking the surface, and these are the points from B, and these are, I'm taking that loops, whatever, which I'm fixing them, and I'm calling that peripheral loops, going once around every element of every point B from the branch locus, and then I'm asking, we have to prescribe. If you want to act by the automorphism group, you have to prescribe the monodromy, so the values of f of gamma I, which are some Ci belonging to G, and you have to fix them, and some very similar theory occurs in this situation, but for the sake of the simplicity, I'm gonna look just to the case when B is empty for the moment, at least. So what we saw the last time is that there is an obvious homological abstraction. An abstraction for homomorphisms, being equivalent. And this is the simplest one. I call it last time the Schur class. So the Schur class of the F is the image of the fundamental class of the surface into H2 of G. So this is the Schur class or invariant. And in this situation, it is invariant. This Schur class is invariant with respect to this action. So it is invariant with respect to the inner automorphism and actually to all automorphisms, by all automorphisms of pi1 of sigma G. Well, let's say automorphism plus to make it simpler. And I also recall that it was a classical by now theorem due, I think, to Livingstone and Zimmermann, saying that in the 80s, 90s, they proved that this is a complete invariant for the stable equivalence. And what means stable equivalence? Recall in a moment. So I'm taking a surface sigma G, Venus G, and now I'm changing it by adding one handle. So I'm adding one more handle. I'm transforming in a sigma G plus 1. I can see that the handle added along a D, so let's say one whole torus, and you have a map which is crushing this handle. Let's call this match pinch, which is going from sigma G plus 1 into sigma G, which is crashing the one hollow torus. So this extra handle. It's crashing to one point. Okay, so let me say if I have alpha 1, beta 1, alpha G plus 1, beta G plus 1, a standard system of generator, standard system of generators of pi 1 of sigma G plus 1. Let's take here these classes and these classes and here. Okay, then simply the pinch is sending alpha I into alpha I if E is smaller or equal to G, and to 1 if E is G plus 1, and P of beta I, it's exactly the same. Okay, so here we have the same alpha I and beta I drawn up here. So this is the stabilization, and the theorem of Livingston-Zimmermann said that two homomorphisms into onto the same group G is are equivalent with respect to the action of this group, automorphism group. In fact, one of them is proving for the automorphism and the other one for this one, but it's basically the same theorem. It doesn't change very much. One is a little bit more precise than the other, if and only if they have the same Schur class. And working on this, there is a very natural question: what happens when the Schur class is 0? So what if the Schur class is 0? So if Schur class is 0, one might expect there are no homological obstruction to lift such homomorphism. In particular, the question is whether such a homomorphism is lifting to a free group, and in particular, it makes sense to make the following definition: say that F is elementary. If F factors, so F is going from pi 1 of sigma G into G, and now it factors through a free group. Putting this, and I'm not specifying precisely, but it will become clear in a moment. F is a free group. I am not specifying on how many generators and so on. It would become clear that there is a better choice for everything. So is elementary if F factors. F, where F is a free group. And of course, a lot of questions which were interesting for us the last time, like lifting homomorphism into G into, for instance, braid group or whatever it could be. If it is elementary, that would be fine. They will lift because from free group I can go anyway. So now, say, imagine there are f which are not elementary. Let's define another invariant. Let's say the thickness T of f, whose that is the number, the minimal number. Let's say minimal number. Minimal number of stabilization when one stabilization corresponds to adding 1 to the genus needed to make f equivalent. Let's say I'm putting in parentheses, in brackets, equivalent to elementary homomorphism. So there exists always, the sure by Livingston and Zimmerman, there exists a number of stabilizations such that it will become equivalent to one which is elementary, and of course that means it is elementary itself. So this is not really needed equivalent. So what I would like to discuss today is whether the thickness can be positive, and if we can have some information about these equivalence classes for elementary, for non-elementary, and so on. So first remark, just to say that a priori the definition and the discussion is not entirely trivial. Let's say that that's a nice result by Reznikov. I think is 97. In topology says that if G is a free product of groups, let me say, you can take Z, so you get free groups Z over MZ for some n, or pi 1 of M free, where M free admits it's a closed free manifold, closed orientable free manifold, which admits a metric, Riemannian metric of positive scalar curvature. And you can get such examples. For instance, if I'm taking, a group H, finite group acting freely, on S3, there are such groups. For instance, the so-called binary dihedral, binary tetrahedral, icosahedral. Well, there are some. There is a finite list of such groups which act freely on S3. This is the case. Then what's saying the theorem is that all homomorphisms from pi1 of sigma g, g is at least 2 into g, are elementary. Actually, their thicknesses is trivial. There are no other possibilities. This is an amazing theorem, saying that the question about such homomorphisms can depend strongly on the group G, on the properties of the group G, both in the case where G is finite, or it can be infinite when we take free products of such. Okay, so let me give you a first, let's say, easy proposition, which is specifying who's that T of F. So T of F is actually the minimum n such that there exists a free manifold M3 with boundary of M3 identified to sigma G, such that the map going from pi1 of sigma G into G factors through pi1 of M3. And here, this map is actually the map, and I call I star. I star is the map induced by the inclusion. By the inclusion from sigma G inside M3 as the boundary. So actually, that's a geometric way to see. And who's n? Well, n is the Higard genus of M. So I'm taking the smallest, in some sense, the smallest complexity from the point of view of the Higard genus, on which the map F, which we had before, will extend in some sense or factors to the free manifold.
Sorry, can I ask you, in the diagram N, what does it mean? N is a Higard genus, but in the problem, what minimum of what?
There exists the minimum of the Higard genus of all free manifolds with, let me say, the minimal Higard genus over all free manifolds having this property.
So this is so-called minimum number of stabilization to take F. Okay.
Yeah, precisely. And I explained a little bit the sketch of proof last time. Let me show it in this case. It's even more clear, and maybe it's worthy to state it. So you need the Schur class to be 0, because otherwise this is not defined. It's only defined for in this situation. And as I said, by a theorem of René Thom, this F is induced from a map F from sigma G into the classifying space BG, and which is bordant, null bordant, meaning so F star is F in homotopy, and F extends to a free manifold. That the definition of the Schur class somewhat extends to a free manifold. So I'm taking here the free manifold and I'm going this way. And now if I'm looking to M3 and I'm taking a Higard decomposition, and what the Higard decomposition let H K denote the handle body of genus, the handle body of genus K, and also let the H K G denote the compression body. The compression body, what does it mean? The compression body with two whose boundary is the union of sigma K and sigma G. What this means, a compression body, is that for you add one handles to sigma G cross 0, 1, or vice versa, you look at sigma K times 0, 1, and you add two handles. Simple closed curve embedded into one side. So we have then M3 has such a decomposition, a Higard decomposition, is the union along some Higard surface of two handle bodies of this form. And what we observe by it's somewhat by definition that the fundamental group of sigma K will surject into pi 1 of the compression body, and the pi 1 of the compression body, as I said, let me do that picture, sigma G, and somewhere here, sigma K. And here is H A, so here is A G. But actually, this one is very simple. It's is the pi 1 of sigma G, and then you send to the identity a number of classes of simple closed curve, but on the other hand, the meridian remain. So you have here the free group on K minus G generator. And who's pi 1 of M3? Well, that's simple. The pi 1 of HK, the amalgamated product of pi 1 of sigma K with this pi 1 of HKG. So when you have the composition pi 1 of sigma K is going into pi 1 of HKG, and this is induced by the next map is induced by the inclusion into pi 1 of M3, and this is the map into G. That's again, I'm still calling F this map, and this is the map induced in topology. Then this map up here is actually a stabilization of the map, which is going from pi 1 of sigma G into pi 1 of HKG into pi 1 of M3 into G. And this is the F, and this is F prime. F prime is a stabilization. F prime. Yes.
Luis,
Yeah.
why is the fundamental group of the compression body isomorphic to the free product? This seems strange.
Well, it's obtained from a surface of genus G by adding k minus G one handles.
Okay, okay, I see.
Okay.
Yes, yes.
And here, as I said, this is pi 1 of sigma G product F k minus G. And you can see them both up here in one or the other of the line. F prime is a stabilization of F by k minus G stabilization, elementary stabilizations. So it becomes also elementary because F prime, this group is free. Oh, yeah. This is also factorizing through this group because it's go to pi 1 of M free. It factors to pi 1 of H1 of K. It's free. So F prime is going this way. Okay. So it is elementary. And we have obviously the number K is bigger than and equal than T of F plus G. Okay, that's half of the inequality. Let me show you the other part. So conversely, assume we have a map, let's say pi 1 of sigma H now, which is going into, again, let's call F prime, pi 1 of sigma J is going to some free group, free, and then into G, and that this is a stabilization of F. Then we're gonna use something which is rather known, well known. Let me formulate it as a lemma, which I don't want to prove. This lemma was very well known in the 60s and then rediscovered several times. I think it's Zishang, the first who did that in the 60s. Then the specialist of dimension 3, Jaco, and unpublished, of course, spellings somewhere between them. Now it's reproved in several ways. So say that sigma H is, as I said, the boundary of the handle body now of genus H, F of a free group, and we have a map rho from pi 1 of sigma H into some free group. Don't ask anything. Then it factors. So any rho like that, homomorphism, factors in the following way. Factors as, well, pi 1 of sigma H, then is going into pi 1 in sigma H by means of an automorphism phi. Automorphism. I can put even plus always. Then I'm going from pi 1 of sigma H into pi 1 of HH. Okay, that's a map induced by inclusion. Inclusion star. This is a free group on H generators, And now there is some map from here, let's call it Q, into the free group you had already. So up to modifying our row by some automorphism, we always go actually onto the pi1 of the handle body bounded by the surface, namely on the free group on H generators, and from there it goes the way we want into our free group. So I assume this lemma, and well, there are many recent proofs about that, and some basic things about actually surface and free groups, surface group and free groups. And now, once we have this lemma, we can do a construction in a very simple way. I'm taking a free manifold, which is simply H, the handle body of genus H. Now I'm adding the handle body of genus H, or the compression body, the standard compression body. You just add the handles as you like, and now I'm identifying them using the automorphism phi, which is the same as the phi arising up here. Okay, that's the same. So if you really want to be careful, I have to put with the opposite orientation in order to make sense when phi is preserving orientation. If not, everything is switched. And now I'm looking to our homomorphism phi prime, which was a stabilization of F, and I'm using the composition with phi inverse. And now you observe that this is going from pi1 of sigma H into G, okay, and extends to F prime composed phi inverse, extends over M free, actually over pi1 of M free, because the main condition comes from this part here. Okay, so this is precisely saying that F prime from phi inverse extends over pi1 of M free. So which is, yeah, that's the usual amalgamated product. I don't write it anymore. And M free as genus, Higard genus at most H. So actually, what we found is that well, T of F is bigger than equal than H minus G. The number of stabilization is at least H minus G. Then this is proving the other inequality, and is getting a short proof. Well, I didn't say anything very deep up here. It's just a way to rephrase the proof of Livingstone and Zimmerman in more geometric terms. Now let me try to express this in a purely algebraic terms now, and to do that, I'm adding some more algebraic definition. How to encode? I wish to encode such a homomorphism F from pi1 of sigma G into a group G. by taking alpha I, beta I, this generator system. Let's say standard, but never mind, generator system. And I'm taking the image f of alpha. Well, let me change the notation, sorry. Let me take AI and BI, such that f of AI is some alpha I, an element of G, and f of BI, it's beta I still in G. And G now has a group presentation, so it's some free group F divided by the normal subgroup R generated by relations. So that group presentation for the group G. So I'm looking to alpha I tilde and beta I tilde in lifts, arbitrary lifts in a priori arbitrary in F, lifts of alpha I and beta I, which were elements of G. To such a structure, let's call such a structure S tilde, the system of, well, it's not generators, but generators for the image. And I'm defining something which I don't remember why I used the notation OCL, but it has to say something, but I really forgot. So I'm taking the minimum of n with the property that there exists Rj in the group R, Fj in the group F, such that the product of the commutator Rg and Fj from J1 to N, it's actually the product of alpha A tilde and beta A tilde from 1 to G. And OCL of the, let's say, of F is the minimum possible of OCL tilde over or S tilde. Actually, it's only S tilde which really matters. So that's sound a bit crazy. It's a way to.
Sorry, can I stupid question? We expect that n is less than G. Yes, G is great number, and n should be less, more economical. Or what we are expecting?
Let me say it the following way. We have the Hopf formula. The Hopf formula for H2. If H2 has this kind of presentation, H2 of G has also a kind of presentation, which is, if I will remember, you take the commutator of F, intersect it with R, and this is the free group, and here you put FR. So what I am actually claiming is that because sure of F is a class which vanishes here, that means that if we represent the sure class as an element of this form in H2 of G, then it belongs actually to, so if we find two cycle representing Schur of F in this group, then it actually belongs to this. And well, the product I'm writing here, you actually, the Schur class, you can represent it. I'm not putting equal, but represented by this element, which belongs, as I said, both to FF and both R. So this element we know because our Schur class is 0 in H2, we know that such N exists. Does exist. I don't think there is something else which can be said for general G. But I will say something later. What is expected for finite G? So I don't know much more. What we expect? That's an interesting question. Can N be very big? We actually don't have explicit examples. So that would be an open question. What are these ranges for N? So let me state something which again it doesn't seem very complicated, is that actually this is precisely the thickness of the homomorphism F. This is invariant OCL of F. Let me give, no, it's already, I prepared 5 pages and it's almost 1 hour and I didn't go through to the first page of my notes. So I think better to go further if you really want to. I'll explain you the proof later, but this is not very complicated. Okay, it's just some algebra, some basic algebra. Okay, so if you want, I'll say more later. The drawback of this theorem, which is, well, it gives you some algebraic definition for T of F, is that really I'm sorry to say that, but it's somewhat useless. I'm not able to compute with it. This is more or less like the computation with the whole formulas are very hard to be done. So one has still this question. Let's step to the second part of the talk. Are there any non-elementary homomorphism? What is known? So are there non-elementary homomorphism? And this makes sense because, as I gave you this theorem of Reznikov, is saying that for some groups they really don't exist. So, but one thing to observe is that already for the elementary ones, you know that there exists such. Elementary sure exist. If I'm taking pi1 of sigma g, it surjects onto Fg. And if I have a group G, G has at most G generators. Such elementary and surjective map really do exist. So elementary, there exist. There are. And what is known, how many? It depends, of course, of the group G, because I'd like to know how many there are and how this equivalence relations is working. And the thing which motivated me a lot is this Vigold conjecture. It's there's around 50 years, something like that, saying that for any simple non-abelian and take it finite group G, and N is at least 3. If I'm considering the kind of elementary homomorphism up to the right equivalence, so what that? So that is again the autorautomorphism group. I'm taking all of it of Fn, and now I'm taking the homomorphism, which I'm putting at S, meaning surjective of of the free group on N elements and G. And I'm usually putting G. Sometimes one has to put out of G, but in most cases the two are coinciding. Well, actually, there is only one up to equivalence. That's a bit strange. This is meaning that up to equivalence there is only one. The right equivalence being again that by automorphism group of the free group acting on the left, or both acting here. And more generally, there are people who stated in an optimistic way the same should actually hold for N bigger or equal for any finite group G, and bigger or equal than nu of G plus 1, where nu of G is the minimal number of generator. Of the group G. This is a more generalized statement because recall that if G is simple non-abelian, is 2 generated. So well, this I think it's Garion Shelley, who was an ex-student of Lubotsky, who stated it in this way, but yeah. So this conjecture is saying that there is essentially one orbit and nothing else for the elementary epimorphism. Now that there are some results supporting this conjecture. Let me state some. Some old results in the 70s already, saying that, so I think is Gilman Robert Gilman, 77. Evans completed it. I think if Gilman did it for n at least 4, and Evans extended also to n equals 4 sometimes in 93. He's saying that for any finite non-finite simple non-abelian G, you have the group automorphism of Fn acts as the alternating. So it acts very transitively as the alternating or symmetric group on the set now let me formulate on one large orbit it on S Fn G. So there is one orbit with let's say R elements, and R is going to infinity as n is going to infinity. So it becomes a very large one, and in particular, if G equals PSL2, and now I am still writing an F, but now it's a boldface. This is the finite field, or if you want with Q elements. But I'm taking Q prime, so I take Q prime, so this is Z over QZ. To make it simpler, if G has this form, then this is the full orbit. This large orbit is the only one. So it's just FNG. So what is saying that you have an action of the automorphism group, which has a very big orbit. It can be made more precise than that, but I think it's enough. It's large with respect to the other orbits, and the action is by the alternating group on R elements on it. So it's again it mixed a lot, and this is also working for. This is also true. Is also true, namely only one orbit and so on, if n is bigger than 2 logarithm of the number of elements of G. Well, of course, this is it doesn't say nothing for small n's, but it's saying that for very big n, in some sense, the conjecture of Wiegand holds.
Excuse me.
Yeah.
Luis, what do you mean by acts like a symmetric or alternating group? Actor through an action of symmetric group, or what does it mean?
No, so you have a set of R elements, let's say 1, 2, 3. This is a subset of S. FNG, right? And the action, so out Fn induce an action here. So that means out Fn is sent into the symmetric group on L elements, right? Well, the image
So,
contains the alternating group AR.
The result is saying that there exists such a map to the symmetric group, and the action factors through this map.
No, there exists always, because out Fn is acting on home SFN G. So let's say if G is PSL2 of F cube, that's even simpler. So so that means this is a finite set. So how it acts? It permutes. Every element of out Fn is permuting in this set.
Okay, I see. Mhm.
So this is giving you automatically, because of the action, this map up here.
What does it mean? S, I don't understand.
SR is the symmetric group.
No, home S with upper script S. What does it mean?
Oh, surjective.
Ah, okay.
Surjective everywhere, sorry. Surjective. I'm always using this because I'm just taking surjection, epimorphism. And this is the symmetric group on R elements. So this is saying that it's a big group in the symmetric group. It really not only acts transitively, but in a very strong way. What is known? Well, it's known again that Dun Udi, I think it's in 69, who proved that the action is transitive. Out Fn acts transitively. That's less than saying is a full group, but it's act enough to permit everything transitively if, well, it's like in the conjecture by Shelley-Garian, if n is bigger than the number of generators of G, and G is solvable, finite solvable. Okay, so, well, there is some chance to have results in this direction. Now, there are some other conjectures by McCulloch. I think in this field there are more conjectures than theorems, but maybe that's interesting for at least for young students. He said that any two, they conjecture that any two F prime, as I said, surjectic homomorphism from the free group on n elements into G, where G is finite, become equivalent. Now they are becoming equivalent up to, let's say, out Fn times G after precisely nu of G stabilizations. So nu of G is just the number of generators. That's a number of generators, minimal number of generators of G. Nothing, there are some partial results in this direction, but they are not really breakthrough yet. What can I say that one has again to remark? I think it is, if G is infinite, then Noskov has previously, this is 83 or 81, around there, 81. Yeah. We published examples of, gave counter examples to the analog of this conjecture, meaning there exists G infinite and need n bigger than nu of G, and still need more stabilization, I think, or no, and need at least one stabilization. So the extension of that conjecture by Vigold to the infinite case is cannot be true. That's something which belongs to the realm of finite groups. There is no real explanation for that, and this is related to a lot of questions considered earlier by Walthausen related to the three-dimensional Poincare conjecture and so on. Let me say that to state it as an easy consequence of if Vigold conjecture is true, with the result of Gilman and Evans, and with the fact that actually that large orbit in many cases is the whole orbit, then what he's saying is that plus Gilman, Evans, and not only the existence of one large orbit, but the existence of all orbits are large. That means that if this is true, a consequence will be there is no characteristic simple finite non-abelian quotient. What means characteristic quotient of free group Fn? Well, if I have a group G, well, there is still one G, sorry. If I have a group H, I'm taking K, a normal subgroup of H is characteristic. If invariant by all automorphisms of H. I'm taking H, I'm taking a quotient, let's say F goes into a group G. G is characteristic quotient. If the kernel is characteristic there. Okay, so of course, why does this say that? A characteristic quotient corresponds to the fact that the kernel is invariant by all the automorphisms. So if I'm looking to the associated homomorphism F from the free group into G, and this is characteristic, that means that F is actually an isolated orbit of out of M. Okay, so that's the same as a characteristic. Okay, so that would be the opposite situation with respect to big orbits. Now we have a number of conjectures saying morphing about that, which were made by Lubotsky. Let me state them. Let's say the so-called conjecture C. Say that for any finite G, one stabilization is defined exactly in the same way as for the surface group, but this time we just add one generator to the free group. One stabilization is enough to make surjective homomorphism. Fn into G equivalent. So actually, that's a much stronger requirement that that was done by the conjecture of McCullough and Vanderlei. And why it is interesting? It is interesting because there is no yet any counterexample to this one. I mean, one doesn't know too much about. So everything we know, in all cases, one stabilization is enough to do everything. So with respect to the question about the N we had before in the case of surfaces, well, we don't know anything and any example with N bigger than 1 either. So let me put now another conjecture D, but saying that for any G finite simple non-abelian, so if I'm taking surjective from Fn into G, and at least 3, and at least 3 everywhere, then there exists a free factor H included and not equal, so with Fn. So what means a free factor? I'll say in a minute, such that f of H is still G. That means that if we take, namely, if G1, G is a generator system for Fn, there exists some I such that the group generated by f of G1 f well f g I minus 1 f g I plus 1, so I omit f of gi f gn is still the group G. Now we can drop one generator, we take the restriction, and it's still the same group G. That's quite amazing. So this is exactly the kind of thing Noskov constructed counterexample for infinite groups G. But in the case where G is finite, there is still nothing known about. Another conjecture quite related to that is the so-called conjecture S, saying that if Fn is take a representation which factors to the automorphism group of Fn, and it goes down to is just a finite dimensional representation over C, then the image of Fn, so this is rho, just a linear representation, then the image of Fn is always virtually solvable. This is related to the nonlinearity of the automorphism group of Fn, and I recall you there is some theorem of Formanek and Marchesi, which, by the way, is proving that the automorphism group of Fn with n at least 3, it is not linear. And the way to prove that is that if I'm taking Fn generated by the G1 Gn, then for any A, I, and G, the image rho of the subgroup of two generators Gi, G, J, G is itself virtually solvable. But is not known if the full group has, so this is the free group of two generators inside Fn. Okay. We can ask the same question, so this is known since the 80s. We can ask the same question, and these are very relevant. Ask the same, exactly the same for the homomorphisms which are surjective from pi1 of sigma j into G. Instead of free group. So we are basically in the case where we only consider the elementary such homomorphism, the conjectures above are more or less saying what we should expect for the elementary case. So essentially we are looking for things which are non-elementary. So in this case, the main thing is already to look at the existence of such homomorphism into groups with prescribed properties. And one of them, we saw that it would be interesting to find what happens when G is finite, non-abelian, simple. This is one situation we would like to understand, and especially it was interesting because of that theorem of Gilman. I'm gonna say it again for the case of surfaces in particular, and characteristic. Why? Because characteristic means very small orbit. And again, we can show that from Gilman, there exists always a big orbit. Let me state the theorem. Well, actually, that's an older result by myself and Pierre Lochac. I'm going to explain a little how it works later. There are parts of it which are very technical, and I won't say anything, but the idea of the application is very simple. So you think that for any G at least 2, there exist infinitely many finite, simple, non-abelian characteristic quotients of the group Y1 of sigma G. And in particular, these are not only non-elementary. I'm saying that the quotient is non-elementary if the map, the homomorphism from pi1 of sigma G into G, which is coming with, is non-elementary. And more than that, I would say, well, Reznikov is saying essentially injective. Let's say the kernel is non-geometric. In which sense? It does not contain any class, conjugacy class of simple curve sigma G. So of course the main thing is that you have a simple closed curve, right? Non-geometric kernels were already known. Non-geometric kernels are known since Livingstone in 2010. Oh no, in 2000, I think. Picard considered also simple, I guess. I don't remember exactly. 0, 1. Gabay considered that at the very beginning. What is interesting here is that this provide automatically answered to all the questions above in the case of surfaces. Namely, so of course, at first there exists such finite simple non-abelian characteristic quotients. Okay, that's the first thing, which are moreover non-geometric, so they are non-elementary. So for any G, you have at least 2 orbits. So that's the first corollary. Let me state it. There exist infinitely many G such that the action is at least 2. It's at least 2 because there is a large orbit and there is a very small one and an isolated one. So at least 2, right? Now, of course, we have we need at least one stabilization, because these G here are simple. They have 2 generators, so there is an elementary homomorphism, which a big orbit. You need at least one to make the non-elementary one become elementary. Well, we can say more. We can say that let me note that pi g is pi 1 of sigma g to make it simpler. It embeds into the automorphism group of the fundamental group, and it's sent. If I'm taking, there are some finite dimensional representation. Well, start that the image is not virtually solvable, and the reason is that it contains a free group. It contains a free group on 2 generators. So this is already saying that the analog of the conjectures are not true, and in the case of non-elementary surjective homomorphism has to be considered seriously. That there are some non-trivial examples. There is something which I didn't say, and there are some very recent results by William Chen, which is maybe worthy to be recorded. The case n equals 2 is special because it can be say something with our approach, and I didn't do the work until the end. What happens with the automorphic group of F2 and the auto-automorphic group of F2? Well, these are quite particular. So the automorphic group is GL2 of Z. And the auto-automorphic group is, so this is also the mapping class group. Oh, I don't remember how it's called, the mapping class group of the torus with genus 1 with 1 puncture. So this is 1 punctured torus. And the auto-automorphic group, it appears to be isomorphic to sigma 1, 2 punctured torus. And when I'm taking that, this is the pure mapping class group. In this case, as I said, one has to be careful what happens on the boundaries. And it happens that if I'm taking F2 generated by 2 elements A and B, the class of AB is the conjugacy class of AB, let's call it E, and the conjugacy class of E and E inverse, the two are invariant by automorphism group of F2. This is the analog of course, of the peripheral loop around here. So this class is invariant, and it can be reversed by an element of automorphism group, because this is the way the automorphism is changing the orientation corresponding to homeomorphism, which are changing the orientation of the torus. So this is the right invariant. Actually, it has a name, that's the so-called Hickman invariant and if I'm taking F2 into, let's say, I'm taking G in the simplest case is PSL2 Z over QZ, Q prime. Then there is an invariant, and the invariant is essentially the class of the trace of the f of A commutator f of B, which belongs to Z over QZ. So this is an invariant for the action of out F2. So the question, which goes back again to McCullough and Vanderlei, was that this trace, or the Hickman invariant, which is the conjugacy class in PSL2Z over Q, are determining exactly which are the orbits of out F2 on such homomorphism. And this is true. It became a theorem by William Chen. It's 2 years ago, I think, but it will appear soon, saying that this is indeed true. This is true. There is only one orbit of out F2 if we fix the Hickman invariant inside the conjugacy classes of PSL2 for all but finitely many primes Q. Okay, so I spoke for 1 hour and a half. I can give you some hint about how to construct characteristics, or how these characteristic quotients arise, or yeah. Let me do that. How to construct such characteristic quotients. I think it's 3 or 4. The simplest construction is, for instance, to take the Abelianization of a group. That's a characteristic quotient. Then you take nilpotent quotients and so on. But there is no chance to get simple finite groups this way, or this is what we are looking after. So here is the the idea right now. To construct characteristic quotient, if I'm taking some quotient of pi into G, let's say, here is some row, I see it as a representation. Recall that pi embeds into automorphism group of pi. I'm taking groups like the center is trivial, so this is the center. And here is IG into the automorphism group of G. So if we have here a natural map, a row tilde, row bar, such that this, if this is commutative, such a diagram, then automatically rho is out pi invariant. This is a simple computation because I'm taking IG, I'm taking rho, and I'm acting with, let's say, x in pi, and phi, an element of an automorphism of pi. Then I'm acting by phi of x. And this is the same as rho bar of I of phi of x. So this is a rho bar of phi I of x phi inverse, because I'm seeing that as acting, the embedding is into the inner automorphism. I'm continuing, this is rho bar of phi, rho bar of I of x, rho bar of phi inverse. So this is rho bar of phi I G of rho of x, rho bar of phi inverse. And if this is 1, this implies that IG of rho of x is 1, and because it has no center, rho of x is 1. So that is simply saying that the kernel is characteristic.
Sorry, row bar, what does it mean?
Rho bar is this one around here. So
Okay, I see.
I'm not claiming that it always exists. Okay. So one idea would be to construct such a commutative diagram, and maybe the simplest one is if instead of considering that, I'm able to do even better, to construct such a diagram with such a map here, which is let's say chi, and then I'm defining rho bar as a composition between IG and chi. Okay, so how do you construct such things? So what I really interested is to get something like that. Well, there is a way using linear representations. So I'm explaining you the idea. I'm construct representations, linear representation. of the group of automorphism into some G Lie group, linear algebraic, better defined over the rationals, such that now you have here a group pi, which is embedded here, such that the image of pi is already Zariski dense in G. Why this is enough? We have two very interesting classical theorems in representation theory and the theory of linear algebraic groups. That two theorems are more or less equivalent, but there are two ways to state them. Let me start with the first one, which is over the rational. That's the so-called strong approximation theorem in the version given by Nori in the 90s. If I'm taking G connected linear algebraic, defined over the rationals, and I'm taking lambda, a subgroup inside the group of integer points, G of Z is the points defined over Z G, which is a Zariski dense subgroup. We assume the points of G over C form a simply connected group from algebraic viewpoint. Then the way it states is a little bit fancy, but I'll explain a little bit exactly what does it mean. Then the completion of lambda with respect to the congruence topology induced by from G of Z So this congruence topology corresponds to taking basis of neighborhoods, all maps from G of Z into G of Z over QZ. And I'm taking the kernels of that for all large enough Q for where it is defined. This is the congruence topology. Is an open subgroup. Of G of Z hat. So let me state it in a very much more clear way. That means I state it as a corollary to for all large enough primes P, it makes sense the reduction G of FQ makes sense. That means that the equation defining G do not have appearing denominators which contains P, sorry. Makes sense, and lambda is surjecting into G of FP Okay, the map going from lambda into G of Z and from here to here. It's actually a surjection when you restrict here. So what's interesting is that you don't ask lambda to be a finite index subgroup, but it's just a Zariski dense subgroup. This is the power of this theorem. And Zariski density is something you can get used with. Now, of course, to apply such a theorem, there is also another version due to Weiss failure version by Weiss failure around the same time, which is also for linear groups defined over Q and of zeta root of unity. So in some sense it's more general. Both of them are more or less equivalent because by the restrictions of scalars we can go from one to the other. And the theorem which explains how we get to simple finite non-abelian and so on groups is the following one. As I said with Pierre Lochac, is that for G at least 2, a prime now P I think is, and we need that because otherwise there are a lot of changes to be done. Large enough prime. Then there exist some representations of the mapping class group of the surface of genus G with one point, one marked point. So I recall that this is the automorphism group of the pi 1 of sigma G. Inside some projective unitary group of some space. W depends on P, G, and so on, such that the image of rho P of the fundamental group of the surface, which is contained in its automorphism group, is indeed Zariski dense in PUW, and moreover, rho P of gamma well has order well P for any simple closed curve gamma on the surface. So what we are doing next, as explained above, one has to take some reduction mode Q for a large enough prime Q. So I am taking, let's call this group big G. Then rho P phi G is included into rho P of the mapping class group, and I'm making reduction. So everything is here in this group. I cannot really say into G of Z, is actually into G of ring of integrals, cyclotomic integrals. Let's put D of zeta. Theta to the power P is 1. And I'm taking here the reduction into G of, let's say, taking reduction modulo of prime ideal, and residual field is some, so is z theta by some prime ideal. And here Q is large enough. And what is saying, the theorem is saying that all these compositions are actually surjecting, but this is also surjecting. And actually, the image of the two is the same. So this is exactly what we expected for that construction. Now we have a little bit to either to make a computation or to say the order of rho p of gamma in G of FQ is actually P for infinitely many Q, or Q large enough. So that means that we have such a characteristic quotient, which is it sends all curves into elements of non-trivial order, so there is nothing in the kernel, and on the same time, as G is a linear algebraic group, we can see that G of FQ is actually either some unitary group of yeah, it's actually over FQ square sometimes, and in most cases some PSLM FQ, but here it's for n which are very big, the dimensions which appear. So these are actually simple non-abelian groups. Of course, there are only very particular series of simple finite simple groups of Lie type, but this is enough to obtain what we expected, namely characteristic, simple, and in particular with non-geometric kernel, because there is no simple closed curve which in the image has trivial order. So I think already I got my 2 hours, and I should better stop here and see if you have questions. Thank you very much.
Thank you, Luis. Any questions?
I have a question and I have a comment. Can I? My question is, but probably if I take not mapping class group, but diffeomorphism of surface which preserves spin structure, and then I can do just the same problem. Can I have some successful result on this direction, or this is
the same should hold, the same for every finite index subgroup, and even for some of them which are not finite index. Yes.
And think spin structure is very interesting, but I have no very well understood all the stuff, but I'd like to inform you that my colleague Olivier Sepa from Grenoble have constructed very nice Schur classes, but he works not with mapping class group, with lattices in the torus, and the stabilization is if you take small lattices, you take larger one, and we classify the all the invariant, stable invariant and the answer is very non-trivial. But the conjecture is if we have a control with the group G, and then we will do just this computation of the Schur index of lattices. Physicists do interest only of unstable invariant, and this problem looks very, very complicated. But conjecture is if we have such a reformulation of this problem with Schur classes, with stable equivalent classes, with some proper group, then we have take information from non-stable classification of the. This is super conductive. Some physicists, and my favorite example is we are not able to do on the genus G because I don't know how the problem will posed, but referee says us that we have to take genus G, and my favorite example is claimed battle, and group G is quaternionic group. In this case, I see the relation with computation of stable homotopy group, very simple, and this is charged by pi7, this example, and Olivier example charged by pi2 and pi3, more simple. And so your talk for me was very interesting, but I will be thinking after about this information you give me. We have created 2 papers with Olivier, and I think the problem looks at the first glance related with your, because just Schur classes, stable classification, and then some algebra with control. We are not, I'm not expert with this, but we are struggling to understood more carefully. Thank you very much.
Thank you. If you have a specific question, can you write me
this question to you.
Reference.
I can send you 2 papers with Olivier, and maybe you will see, and then you can ask if we have some relation with this topic, or just I am not. I am not right. If I can, I send you the reference.
I'd be interested to see it and to.
Thank you very much.
You're welcome.
So if there are no more questions, let's thank Luis.
Thank you very much. Thank you for.
Thank you very much.
All right. So then.
All right, Sergey, I keep you informed in the next days.
Thank you, Luis. Thank you.
Thank you. I hope to be more clear than the first time.
All right. All right. Thank you.
Okay, so see you and bye-bye.
Goodbye. Goodbye.
Thank you very much.
Bye. Have a good time.
Good time.